In this second outcome, we turn to Group 7, the halogens. We'll look at what they're like physically, the forces that hold their molecules together, and how their reactivity changes as we go down the group. The halogens are Group 7, and the name actually means salt formers, which tells you a lot about how they behave. The four we study are fluorine, chlorine, bromine, and iodine. Astatine sits below them, but it's radioactive and vanishingly rare. Each exists as a diatomic molecule, so two atoms bonded together like chlorine, which is two chlorine atoms joined up. Every atom has 7 electrons in its outer shell, and they're classic non-metals and strong oxidizing agents. A few terms to start with. A halogen is one of these Group 7 nonmetals that form salts and exist as diatomic molecules. A diatomic molecule is just two atoms joined by a covalent bond, like the chlorine molecule. Van der Waals forces are the weak attractions between molecules caused by temporary shifting dipoles. And volatility is how readily something turns into a gas, so a volatile substance has a low boiling point. Let's look at them in turn. Fluorine is a pale yellow gas at room temperature. Chlorine is a pale yellow-green gas. Bromine is a red-brown volatile liquid that gives off a brown vapor. And iodine is a shiny grey-black solid that sublimes into a striking purple vapor. Two patterns jump out. The color deepens as you go down the group, and the physical state shifts from gas to liquid to solid. Setting that out at room temperature, around 20 degrees Celsius. Fluorine is a pale yellow gas, chlorine a pale green gas, bromine a red-brown liquid, and iodine a shiny grey-black solid. That lines up with the boiling points, which climb steadily down the group. Fluorine has the lowest boiling point and stays a gas, while iodine has the highest and is solid at room temperature. So volatility, the tendency to evaporate, decreases as we move from fluorine down to iodine. Put the other way, melting and boiling points increase down the group. Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid, so iodine is the least volatile and fluorine the most. To explain that pattern, we need to think about the forces acting between the molecules, and those are van der Waals forces. Here's the key idea. The halogens are simple molecular substances, and the forces between their separate molecules are weak. The strong covalent bond is inside each molecule, and crucially that bond is not broken when the substance melts or boils. All you have to overcome are the weak van der Waals forces between molecules. Now, the more electrons a molecule has, the larger the temporary dipoles it can form. Iodine has far more electrons than fluorine, so its van der Waals forces are stronger, and stronger forces need more energy to pull apart, which raises the boiling point. Let's apply that. Why is chlorine a gas while iodine is a solid at room temperature? Both are simple molecular, made of separate diatomic molecules held by weak van der Waals forces. But an iodine molecule has many more electrons than a chlorine molecule, and more electrons mean larger temporary induced dipoles, and therefore stronger van der Waals forces. Those stronger forces between iodine molecules take more energy to overcome, so iodine has much higher melting and boiling points. That's why iodine is a solid and chlorine, with weaker forces, is a gas. Now to the reactivity, which starts with electron arrangement. Every halogen atom has 7 outer electrons, an s2p5 outer shell. Fluorine is 1s2, 2s2, 2p5. Chlorine adds a shell to reach 1s2, 2s2, 2p6, 3s2, 3p5. Each one is just a single electron short of a full outer shell, so they react by gaining 1 electron to form a 1- ion, like the chloride ion. Gaining an electron is reduction, so in doing this the halogen is acting as an oxidizing agent. The reactivity of the halogens decreases going down the group, which is the opposite of what we saw for the group 2 metals. Fluorine is the most reactive and iodine the least, so the order of oxidizing power is fluorine, then chlorine, then bromine, then iodine. The reason is size. Down the group, the atoms have more shells and a larger radius, so the outer shell is further from the nucleus and better shielded. That means an incoming electron is attracted much less strongly. Let's unpack that explanation. Reactivity here depends on how easily an atom can grab an extra electron. As we go down, more inner shells increase the shielding of the nucleus, and the outer shell is further from that positive nucleus as well. Both effects weaken the nucleus's pull on an incoming electron, so the atom gains an electron less readily and is a weaker oxidizing agent. Electronegativity, which measures that pull on electrons, therefore also decreases down the group. Let's reason through a comparison. Why is chlorine a stronger oxidizing agent than iodine? Oxidizing strength depends on how readily an atom accepts an electron. An iodine atom is larger than a chlorine atom, with more electron shells, so its outer shell is further from the nucleus and more shielded. That means iodine's nucleus attracts an incoming electron only weakly. Chlorine, being smaller with less shielding, pulls that electron in more strongly, so it gains an electron more easily and oxidizes more powerfully. Hence, chlorine is the stronger oxidizing agent. Time for a quick check. Can you state the trend in volatility from fluorine to iodine and name the force responsible? Why does an iodine molecule have stronger van der Waals forces than a chlorine molecule? Can you write the outer electron configuration shared by all the halogen atoms? And can you explain, in terms of atomic radius and shielding, why reactivity falls down group 7? One neat way to confirm the reactivity order is a displacement reaction. A more reactive halogen will displace a less reactive halide ion from solution, which confirms the order fluorine, chlorine, bromine, iodine. So chlorine can displace both bromide and iodide ions. Bromine can displace iodide but not chloride. And iodine, the weakest, can't displace either chloride or bromide. These are redox reactions. The halogen is reduced while the halide ion is oxidized. Picture what you'd actually see. Add chlorine water to potassium chloride solution and there's no change. But add it to potassium bromide and it turns orange as bromine forms. And to potassium iodide, it turns brown, then grey-black as iodine appears. Now add bromine water instead. Nothing happens with potassium chloride or potassium bromide, but with potassium iodide, it turns brown as iodine is displaced. The colours tell you exactly which halogen has been set free. Let's put those on paper. Chlorine plus potassium bromide gives potassium chloride plus bromine. Chlorine plus potassium iodide gives potassium chloride plus iodine. And bromine plus potassium iodide gives potassium bromide plus iodine. If we strip it down to the ionic equation, chlorine plus bromide ions gives chloride ions plus bromine, and similarly, chlorine plus iodide ions gives chloride ions plus iodine. The potassium ions take no part, so they're spectator ions, and we leave them out. Let's write half equations for one of these. When chlorine water is added to potassium iodide, iodine forms. Chlorine gains electrons, each chlorine going from 0 to -1. So chlorine plus 2 electrons gives 2 chloride ions. That gain of electrons is reduction, making chlorine the oxidizing agent. Meanwhile, the iodide ions lose electrons, each iodine going from -1 to 0. So 2 iodide ions give iodine plus 2 electrons. That loss is oxidation, making iodide the reducing agent. Both halves involve 2 electrons, so they combine straight into chlorine plus 2 iodide ions gives 2 chloride ions plus iodine. Step back and see what the displacements are really telling us. In each case, the halogen pulls electrons off a halide ion, and a halogen can only do that to a halide sitting below it in reactivity. Chlorine oxidizes both bromide and iodide because it's the stronger oxidizer, while iodine can't touch chloride or bromide because it's the weakest. This is exactly the pattern we explained using atomic radius and shielding. In the lab, adding an organic solvent makes the color of the freed halogen easier to identify. Some terms to lock in. A displacement reaction is where a more reactive element takes the place of a less reactive one. A half equation shows just the electrons lost or gained by one species in a redox reaction. A spectator ion sits in solution but takes no part in the reaction, like the potassium ion here. And disproportionation, which we'll meet shortly, is a reaction where the same element is both oxidized and reduced. Here's how we test for halide ions in the lab. First, add dilute nitric acid, then silver nitrate solution to the sample. The nitric acid is there to remove any carbonate ions that could otherwise give a misleading precipitate. The silver ions then react with any halide present to form a colored precipitate. Chloride gives white silver chloride, bromide gives cream silver bromide, and iodide gives yellow silver iodide. Those three precipitates can look quite similar, so we confirm them with ammonia. Silver chloride is white and dissolves in dilute ammonia. Silver bromide is cream and only dissolves in concentrated ammonia. And silver iodide is yellow and won't dissolve even in concentrated ammonia. So the color gives you a first answer, and the ammonia test settles any doubt between them. Let's use that. A solution gives a cream precipitate with acidified silver nitrate, and that precipitate dissolves in concentrated ammonia but not in dilute. Which halide is it? The cream color points to silver bromide straight away, since white would be chloride and yellow would be iodide. Then we check the ammonia results. Silver chloride would have dissolved in dilute ammonia, so it's ruled out. And silver iodide would stay insoluble, even in concentrated, so it's ruled out too. Silver bromide dissolving only in concentrated ammonia fits perfectly, so the ion present is bromide. Chlorine has a hugely important everyday use, purifying drinking water by killing harmful bacteria. When it's added, it reacts reversibly with water to give chloric 1 acid, also called hypochlorous acid, plus hydrochloric acid. That chloric 1 acid is the actual germ killer. Interestingly, this is a disproportionation reaction. The chlorine starts at oxidation state 0 in the chlorine molecule and ends up at +1 in the chloric acid and -1 in the hydrochloric acid, so it's both oxidized and reduced at once. Let's prove that's disproportionation using oxidation states. In the chlorine molecule, each chlorine atom is at 0, since it's an uncombined element. In hydrochloric acid, hydrogen is +1, so chlorine must be -1. In chloric 1 acid, hydrogen is +1 and oxygen is -2, so chlorine works out at +1. So one chlorine atom falls from 0 to -1 and is reduced, while the other rises from 0 to +1 and is oxidized. The same element being both oxidized and reduced is precisely what disproportionation means. Chlorine does something similar with cold, dilute sodium hydroxide, and this time we make household bleach. The equation is chlorine plus 2 sodium hydroxide gives sodium chloride plus sodium chlorate 1 plus water. That sodium chlorate 1 is the active bleaching agent. Once again, it's disproportionation. The chlorine goes from 0 to -1 in the sodium chloride and +1 in the sodium chlorate. The resulting mixture is what we use as bleach and disinfectant. So we've seen two disproportionation reactions of chlorine side by side. With water, chlorine and water give chloric 1 acid and hydrochloric acid, with chlorine going to both +1 and -1, and that's used to purify drinking water. With cold, dilute sodium hydroxide, chlorine gives sodium chloride, sodium chlorate 1 and water, again going to +1 and -1, and that's used to make bleach and disinfectant. Same chemistry, two very useful outcomes. It's worth weighing up chlorination honestly. On the benefit side, chlorine kills the bacteria behind diseases like cholera and typhoid, and it keeps working, giving lasting protection as water travels through the pipes. On the risk side, chlorine gas is toxic and irritates the eyes and lungs, and it can form small amounts of chlorinated organic compounds. On balance, though, safe drinking water saves far more lives than those risks cost, and it's a good example of halogen chemistry directly supporting public health. Let's check your understanding before we finish. Can you write the balanced equation for chlorine reacting with cold dilute sodium hydroxide? Using oxidation states, can you explain why chlorine reacting with water is disproportionation? Can you state the colors of the silver halide precipitates, silver chloride, silver bromide, and silver iodide? And how does their solubility in ammonia help you tell silver bromide from silver iodide?